and welcome to today's edition of Cracking the Cryptic, where today we are revisiting the puzzles of Joseph Nehme, a name that will be familiar to many of you. Joseph's puzzles, I don't know how many times Joseph's featured on the channel, but it must be at least a dozen. Joseph's puzzles are always beautiful, and normally, actually this is interesting, they're normally quite approachable. I say quite because they often contain very original logic, but this puzzle has proved a bit of a stumper. We've had it requested a few times, both by people who've solved it and said it's beautiful, and by people who've tried it, seeing it's only got 3 stars out of 5 for difficulty on Logic Masters Germany, and have failed utterly. So we are going to see whether we can get through it in a moment. I will tell you that 2 of our testers did not manage to solve this, so it probably has some trickery in it. It's basically just an arrow Sudoku though, with a diagonal constraint, so I'll read you the rules in just a moment. Do I have any news for you today? I don't think I do, actually. So yeah, just a reminder really, if you enjoy our content, do check out our apps. We are very, very proud of them. We have a whole suite of Sudoku apps, all crammed full of handcrafted puzzles from some of the best setters in the world. If you go to the App Store, you'll find them. Or Google or the Android store, whatever it's called, or even Steam. It's available everywhere, or they're available everywhere. And yeah, as I say, we've worked very hard on them over the years, and we hope that you enjoy them. Other than that, there's Patreon, of course, for loads of extra content. There's the Discord server, where it must be the biggest puzzle community in the world. It just must be. Some 25,000 people are members of the Discord server now, all exchanging ideas in a delightful way. It's a community we are very, very proud of. Now, and that's all the news, just to tell you all that. So let's have a look at where now, which is an interesting question by Joseph, and these are the rules. Normal Sudoku rules apply. Digits along an arrow must sum to the digit in that arrow's circle. So let's pick this arrow. Let's imagine this was a 1, this was a 2, and that was a 5. 1 plus 2 plus 5 equals, 8. So you'd have to put 8 in the circle. So just make sure that the sum of the digits along the arrow add up to the circle, and you'll be good to go. A digit cannot repeat on a main diagonal, each marked in blue. Okay, so that's telling us these 9 cells here all have to be different digits, and the same is going to be true for these 9 cells on the negative diagonal. It's called the negative diagonal because if on a graph of y versus x, this would have a negative gradient, so this is sometimes called the positive diagonal for a similar reason. And the cell containing the opaque grey circle contains an odd digit, so this cell has to be odd. I doubt that that's going to answer the question where now, because I suspect this has been put in to disambiguate the very end of the puzzle. We shall see. But do have a go. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. And I will start with this arrow, I was going to say, because I can see that this is the sum of 3 different digits. The minimum I could put into those cells would be 1, 2, and 3. So this must be at least a 6. Can't type. Now that one's a bit annoying actually. That's a little bit different, look. Because this one is the sum of 3 arrow cells, but these are not in the same box and they don't see each other through the mechanism of Sudoku. So what you could do there is that, rather annoyingly, which means that the minimum sum of this arrow is 4, and that doesn't deserve to be pencil marked therefore, because basically it's let itself down. That's another 3-cell arrow here though, so that's another 6, 7, 8, 9. Those 3 digits do have to be different. Right, so what on earth is going on here? Okay, there is a small point. Well, potentially it might be a big point. I'm not sure yet. But let's have a look at this digit. Well, no, not that digit, more that arrow. Let's have a look at this arrow and these arrows. Now you can see that these cells here are all, oh, that's a horrible colour to have chosen, sorry, I used blue. These cells here are all in the same row. So the minimum sum that these digits, the blue digits, could have would be a 1, 2, 3, 4 and 5. And 1, 2, 3, 4 and 5 add up to 15. So that means these two circled cells add up to 15 at least. And that means that we can't make this even as low as 5. This must be at least equal to 6. Okay. I can totally see actually why people have had trouble with this, because whatever it is about the puzzle that's meant to allow you to break into it it looks elusive. We've got lots of short arrows. Like, it's interesting. This arrangement here, obviously that's telling us those two cells are the same. And that might be important, but it's not clear to me it's important at this point. You know, I can see red has to be in one of those 4 cells and one of these 4 cells. The same is true of this arrow, look. Again, we know those are repeated digits. So they must appear down there. But we know very little about box 9. In fact, the corner boxes in general are rather they're rather desert-like, aren't they? There's not a lot going on. Yeah, in terms of the action in this puzzle, it looks like the action is in column 4 and row 5. It could be set, this, actually. That's often what happens when you know, if you are totally stuck on a puzzle, it can sometimes be worth considering set. Wow, I don't know. I think I'm missing something probably more obvious than set though here. And if we were going to think about set, what should we be looking at? That's a good question, isn't it? I don't know. I don't know is the short answer. Golly, okay, I'm doing appallingly badly, and I'm going into one of these sort of catatonic states where I don't speak, which I don't like doing, but it's a symptom of the fact that I'm stuck. I think I'm going to have a look at... Well, I'm going to get rid of this highlighting for a start. If I'm going to do set, I need to think about something different. I can't decide whether... The idea of basically of set, especially in arrows puzzles, is to find equivalent sets of digits where you can get the circles into different sets as compared to the arrows. Yeah, I mean, maybe that row, maybe. So this blue line represents a set of the digits 1 to 9, because we know that row 5 will be a set of the digits 1 to 9. So if I highlight that against that, the orange cells are obviously also a set of the digits 1 to 9. So some people like to think about this in terms of Scrabble bags. You may remember a puzzle we did a few months ago called the Scrabble Bag Equilibrium. I want to say by Olimar, but that might be wrong. And anyway, so if you imagine that we wrote the blue digits on Scrabble tiles and put them in a bag, a blue bag, and we wrote the orange digits on Scrabble tiles and we put them in a bag, obviously both bags contain the same digits at the start of this exercise. Now if I fish around in the bags and I find this digit, that digit's clearly in both bags. It doesn't matter what it is, but it's clearly in both bags. So I could find it in the blue bag and find it in the orange bag and throw it out of both bags. And the result would be that my blue bag would contain 8 digits now, not 9, and my orange bag would contain 8 digits, not 9, but those digits would still be the same. We don't know what they are, but we know they're the same. The same is true of that, the same is true of that. So we can reduce it very quickly to this. It doesn't really require set. But now I'm seeing that. So now imagine that you go into the blue bag and you add up all the digits on the tiles in it, and you do the same with the orange bag. Clearly you're going to get the same number. Well, a property of the arrows is that these 3 digits here add up to this circle. So if I was to take those digits out of the blue bag, boom, and I was to take this digit out of the orange bag, boom, then we end up with a situation where we now have an unequal number of tiles in the bags, but we still know the totals of the tiles in each bag must add to the same number. I think all I'm doing... Oh no, I'm not. I know this is better. This is. I have proved one thing here. I think I've proved one thing, because now what I can do is I can note that the total of these blues is the same as the total of this. So I could take these out of the blue bag and replace them with a tile with this number on it. And now I know that these orange digits add up to these 2 blue cells. But the orange digits must add up to at least 15, because they're all in the same box. They have to be different, so they could be 1, 2, 3, 4 and 5 at a minimum. So these 2 cells have to add up to at least 15, which means this cell is at least a 6 now, which I didn't know before. At least I don't think I did. I would have known that before if I could have assumed these... No, that's not true. Well, I would have known this could have been 6 if I could guarantee there's no repeated digit on this arrow, but I don't see how I could know that. Right, hang on a minute. Can I do Sudoku now? Or is that unreasonable? What I'm just wondering is where that digit, let's make it green, where that digit goes in this box. Because green can't go in here by Sudoku, and it can't go on its own arrow. Because if this was green, it would mean both of those squares would have to be 0 in order for the maths to work. So this green goes in one of those cells in box 4, which means it is in one of these cells in box 6. Now, is that... I don't know. I want to see whether I can argue whether this green can be on this arrow. Because obviously if this is at least 6, if it's on this arrow, this is higher. So this would have to be at least 7 then. So this could be 1, 6. This would be 7. And then no, this is not how to think about this. There is something going on, but I've only just worked out what it is. The question is not to focus on this digit, I think. I think we have to turn this round. I'm going to get rid of the green highlighting for a moment because I think it's going to confuse me. Right, let's instead look at this digit. And let's ask where this digit goes in box 6. And this is interesting, actually. It's really interesting, because if the red digit, which we know is not in these 3 cells, if the red digit was in an orange cell, then we would know, let's just make it there for the sake of argument, because we know these 2 digits sum to these 5 cells, if these cancel out, then this digit is the sum of those 4 cells. But that's impossible because these are 4 different numbers and must add up to at least 10. 1 plus 2 plus 3 plus 4 adds to 10. So that doesn't work. So this red digit, well, the red digit here must be in that cell. And that's weird because when I approached the question from this side, I couldn't prove that. But now, approaching it from this side, I can see it. I don't know whether that was me being daft or just it's a slightly different way of, I think it's a different way of thinking about it. So now red, this red digit must be in one of those cells. Oh, that's lovely. And it's not here. Because if that was red, this is red by reflection on the arrow and it would clash in column 4. So that is not red. So red is in one of these 2 cells. Now, does that logic work the same way for this digit now? What I'm thinking there is, what would happen if this digit was here or here? We know it can't be here because these digits are the same, and we can't have 2 digits the same in box 6. But if this digit was here, that would be saying these 4 digits add up to that one, which we know is impossible as well. So this blue digit, oh, I need to give this a new colour really. Actually, let's get rid of blues. So this digit goes in one of those cells and then goes up here, which... Oh, okay, I think that's not so, that doesn't look so good actually, does it? Right. So what on earth does this mean? That is the question. That is the question, and I don't know the answer. So, golly, I mean that felt like a bit of a breakthrough, didn't it? But it's not done anything. I know these cells are in here. Can I? Is red somehow limited in this box? Look. I can see this can't be red. And if red is on this arrow, then because red is at least 6, this would have to be a 9. Which it could be, I think. So... wow, okay, got nothing. Got nothing here. I haven't thought about the diagonals though, so perhaps this is a good time to think about those. Although, right, I've got red on this diagonal, so red cannot go in any of those cells. So red can't. Okay, red. No, I'm not seeing anything actually. Red. I don't think I can use that I've got to put red on this diagonal somewhere. Okay, so it's got to be in one of the it's got to be in one of those 5 cells. Right, got it. I've got something interesting. Right, look at these the combination of these 2 digits, and ask where. Yeah, this is very cunning. This is very cunning indeed. These little cells here are absolutely pivotal for this logic I'm about to show you. Where does red go in this box? And the answer is basically I haven't got a clue, but I know red can't go on this arrow. So that, because if it did, it would have to be accompanied by the 0. So red's in one of these cells. And where is red in this box? Well, it's the same logic. You can't put it here because you'd have to accompany it with 0s on the arrow. So red is in one of those cells. And that means we can ask where red goes in this row. because we know it's not there and we know it's not in those. So it's in one of these, and it can't be here because of the diagonal. So red is in one of these cells, which means red in this column is not in these 6 cells, and it's not here because then red would reflect there and repeat in column 4. So red is on the arrow, and that is huge because that's told us the nature of redness today. The nature of red today is it must be a 6 because it's at least a 6, and you can't have more than a 6 on a 3-cell arrow. So this arrow is 1, 2, 6. That is a heck of a break-in. And this is a 9, and therefore that's not, well, we know red is 6. We've just worked that out. So red is 6. This is not 6. So, right, well, at least that gets us some things, doesn't it? Because red on an arrow must be 1, 2, 3. Oh, this is beautiful. Right, look at this. So this is 1, 2, 3 on this arrow to add up to 6. Well, what are those 2 squares then? They can't be 1, 2, and 3. So the lowest they could be is a 4, 5. They couldn't be any more than that, or this would be a double-digit number. So that's a 9, which means it's the same as this. So this is now yellow, which means this is not yellow. One of these is a 6, so that's not a 6. These digits have got to be 7, 8, and 9 to complete. Yes, 7, 8, and 9 to complete this row. That's correct. This arrow and this arrow both add up to 6 in total. So this is either 1, 5 or 2, 4. But this one is more complicated because there's the possibility of a repeated digit here. Although no, there isn't. There isn't actually. That's really interesting. So if we do try and repeat a digit on this arrow, how would we do that? Well, these 2 would have to be the same because this digit sees the other 2, so this can't repeat. But if these 2 repeat, the only digit that could repeat is a 1, because if we repeat 2, this would also be a 2, and that will be a big problem. So the only digit we can repeat is 1, but that makes this a 4. And now this arrow is impossible because it can't be 1, 5 and it can't be 2, 4. So this arrow does not have a repeated digit on it, and therefore it is 1, 2, and 3 in some order. Now, this can't be a 1, 2 pair because that will break this 6 arrow as well. So there's definitely a 3 up here, which means this is not a 3. I see, right. Okay, and now this circle has become under pressure. Because if we think about what this digit has available as its options, we know there's a 1 or a 2 in that domino, and we know there's a 1 or a 2 in that domino. So in effect, these 4 cells definitely contain 1, 2, and 3, and either 4 or 5. Well, that means the minimum this can be is 4. But then the minimum that cell can be is 4 because it sees a 1, 2, 3 triple. So this is at least 8. And these digits cannot be higher than 5 then, because obviously 6 plus 4 is 10. So this is either a 4-5 pair or a 4-4 pair. I don't know if we can tell which of those is true, but this can't be 6 anymore. So we can get rid of the redness that was afflicting this cell. I'm not sure. So there's that. Yeah, okay, so these are, right, yes, of course, these digits are now 1, 2, 3, 4, and 5, which means these digits are 6, 7, 8, and 9, and that's probably huge, because that can't be 6 or 9. So this is down to, this can't be 6. Oh, nearly, that's nearly beautiful, but not quite. Sort of, okay, nearly beautiful. but still a little bit unsymmetrical. So, okay, so what do we do next? I've not used these yet. I've not used this, right? Oh no, okay, I can only eliminate one from here. So yeah, I shouldn't probably get excited about this. This is very likely to be a late disambiguator. Oh bother. Alright, so what am I meant to see now? That is a good question, and I don't know the answer to it. So this digit here, it can't be 1, 2, 3, but it can be, I think it can be 4 or 5, I think. It can't be 6, it would see itself. 7 or 8 maybe? Does that affect this one? I don't think so. One of those options will be eliminated by whatever happens up here. No, I've got a feeling. Again, I've got this feeling I'm missing something here, but I can't see what it is. How disappointing. Okay. Let us instead consider. What on earth am I missing? Is it the diagonal again? I've got 1, 2, 6 here. Or actually, maybe it's this arrow. Okay, sorry, yeah, because this arrow, of course, is reflecting. It's a bit like this one. So these two cells, so this cell can't be 1, 2, or 6. But I don't think that's a particularly interesting reduction in its options. Unless I'm missing something. Oh, okay. Alright, let's actually explore this because I've just noticed something very minor. 3, 4, 5. Can't be 6, 7 or 8. It can't be 3. And it can't be, whoa, it can't be 3. Because if it was 3, this would have to be a 1, 2 pair and that would break that cell. So this is 4, 5, 7 or 8 as well. So there is a 4, 5, 7, 8 quadruple in column 4, which means these cells have to be 1, 2 and 3. Which does absolutely nothing, I think. Oh, bother. Alright, so that was nearly interesting. Nearly, but not good enough. Oh dear. So how do we make more progress now? That is our next challenge. And why can't I see how to make progress? That's not able to be 9 anymore. Okay, so we've got 9 definitely in one of these cells. Oh, yes, okay. Here is a small point. So, if the 9 is in these two cells, where is the 9 in this box? And the answer is, I don't have a clue, except it's definitely, I want to say, in one of those 4 cells, which means 9 in this column is in these top 3 cells. But, similarly, if we look along this row, where is the 9? Well, it's in these 3 cells. So the only cell that meets both of those criteria is that one. And we get a 9 on the diagonal, which means this is not a 9, which means that loses its yellowness, which means this is a 9, and that gains yellowness. So, does that mean this is a 9 at the top of the grid? Don't know. Oh, I've got a 7, 8 pair on this diagonal now, so that is not 7 or 8, which means this is not 7 or 8. Oh, right, this is absolutely beautiful. Right, I love... Oh, right, this is my favourite bit of this whole solve so far. Right, look at this. We've got 4, 5 pairs here. But in this instance, it's subtly different, because these are the same digit because of the arrow. So how could these both be 4? If these were both 4, those are both 5, and this would add up to 10, and that doesn't work. So this must be double 5, which means this is double 4 and adds up to 8 and puts 9 at the top of the grid. That is so beautiful. This 8's given me an 8 here and a 7 here. Oh, that gives me an 8 here, actually. I absolutely love that. That is so... It's so elegant. I mean, imagine making the choices that get you to that point. Joseph, again, just... Oh, this is... Look, this is all getting done now. So this is a 7. This isn't... I was going to say that means that's an 8. No, it doesn't. It means that's a 7 as well. These are the same digit. So 7 has a home up at the top of column 6. These squares have got to be quite low, haven't they? Because they've got to add up to 5. So these have got to be 1s, 2s, 3s and 4s. This is sort of... Oh, right, this is a 6. Because in making a 5 from a domino, you either have to use a 1 or a 2. It's either going to be 1, 4 or 2, 3. And the other 1 and 2 is in that cell in this row. So this can't be a 1 or a 2 as well, or we'd never be able to make this 5 work. So that's a 6. That loses its redness, I suppose. 6 is quite restricted in here. It's got to be in one of those positions, I want to say. This 8 is meaning we've now got a 6, 7 pair over there, which might be important somehow, some way. I don't know. 8 has got to be up here. Oh dear, it's all going wrong now, isn't it? Let's yellowify the 9 in case that, and yellowify this 9 as well in case that fills in some thoughts. So yellow, 9 has to be in one of those 2 cells in box number 3. Can 9 be on the diagonal? Is there some restriction there? 9. Oh, 9's already made a home on the negative diagonal. So 9 is... Oh, so 9 is locked into the same positions as 6 is over here. 5 has to be in one of these by Sudoku. Oh, 7 and 8 may be in this box. Look, they are on this diagonal. So 8 has to be in one of 2 positions. Look at that. Oh, this is good. Right, let's give me another digit. So 8 and 7 are in those 3 cells somehow. But the 8, where's the 8 in this box? And I don't know, but I know it's in one of those 4 cells. So yeah, so the question I could have asked a while ago, look, is where's the 8 in this column? It must be at the very top, just by Sudoku. And therefore this square is a 1, 2 or a 3. 8 has not made an appearance on this diagonal, look. So 8 is in one of those 3 cells and it's not there. So 8 is in one of 2 cells now. Still, oh yeah, okay, I can do that. I can do that. Because 8 in this box, in box 8, is in one of these 2 cells. Now that is aligning with where the 8 is going in box 7. So again, we know in the bottom row, the 8 can't be in these 6 cells. We've just worked out it's got to be in one of those 2 cells, so it's got to be there in the corner, which means there's a 5 in one of these. 8 goes here by Sudoku. 8 goes in one of these 2 cells, which is alongside its friend the 9. So that becomes an 8, 9 pair. And maybe this is going in the right direction now. Oh yeah, look, I've missed something here, something simple. In this box, where does 7 go? Well, not only is it not in any of those cells, but there's a 7 there looking at that one, so that's a 7. Which means that's a 7 and that's a 6, which means that's a 6, so we can de-redify some other cells, look. And we can re-redify these ones and make that one a bit more look like it's dressed properly. Okay, so these are no longer 7, obviously. 8 is now placed in this box in that cell using our pencil marks, which means this is 8, this is 9. So 9 gets re-yellowed. Whoops. And 8 gets un-yellowed. So 9, is there a 9 on this diagonal? We don't know yet. So 9's definitely not there though. So 9 is in one of 2 places. This cell is not a 7. So this is 3, it's not a 5 actually. This is just 3 or 9. So we've almost reached the point at which this is revealing its secrets to us. That cell's a 5 by Sudoku. That gets blued. There's a 5-7 pair in box 9 by Sudoku. So this corner digit is a 1. Oh, this corner digit's a 3 or a 4. It sees a 1-2 pair. So this square is... Yeah, oh, I see. Right. Okay, so... Yeah, so 9 has been squeezed now in this box. It's got to be in the circle, which means that becomes yellow, which means these are not 9s anymore. 9 seems to have to go here by Sudoku, which means 9 goes here by Sudoku. This is lovely. And we've moved the 6 up to there. So does that matter? So 6 in this box is, I think, only in that position, if I trust my reddening of the rest of the grid. And I think I should. Yeah, and now the positive diagonal needs a 6 on it. Where is that? It has to be in the corner, and I think that might give us all the 6s. Let's see. Certainly it gives us the one in this box that has to be there, which shunts the 7 upwards. So that gets a colour. And I've not put a 6 in this box, which has to go exactly here. That's brilliant. Okay, so therefore we have all 6s done. We have all 9s done. This is not an 8 because we've got the 8. 8s we've done... we can do all of just by filling in the last of them. This square's got to be a 3 or a 4, I want to say, to complete the box, which means this cell is not a 3. So there's a 1-2 pair in the middle box now on the diagonal. Still unresolved. But I've got a 1-2 pair in row 4 now, so I need 3, 5 and 7. So this is a 3 or a 5. This... Oh, where does 5 go? That's the question. You can't put 5 into these because of this 4-5 pair, so that's a 5. Which means this is not a 5, which means this is not a 1. Because these add up to 6, obviously. So these... What are we left with here then? 3s and 7s. Into these 2 squares. I think so. I'm just pausing because I can't see how to do that. And I'm surprised. Okay, so this is a 1 or a 2, which gives us a 1-2 pair here. So this is a 3 or a 4. It's going to be something to do with the diagonals, I think. I hope. Okay. These have got to be 1s, 2s, 3s and 4s. I can see that. There's 1s, 2s, 3s and 4s all over the place. But how does it actually get fixed? That's the thing that's bothering me. Because there must be a way. There's probably an arrow I haven't added up or something. No, that's not it. Oh dear, this is suddenly getting a bit worrying. 7s. I've not done all the 7s I could have done. So how do I improve on that? I put a... yeah, look, I can actually. 7 has to be in one of those 2. And that's aligning with where 7's going in box 6. So we can ask where 7 goes in this column now, and it's got to go at the bottom. So that's 7 and that's 5. I don't know, actually. I'm not sure that has done it. So this has got to be 1, 2, 3, and 4. So we've not managed to put, okay, so I've not managed to put 5 on the negative diagonal. That's perhaps an important point, because that means that's a 5. Let's bluify it. These squares are all, you've guessed it, 1s, 2s, 3s, and 4s, all over the place. Okay, so has this 5 done something? Yeah, that's beautiful, isn't it? This 5. So now look at 5s and how they're operating on this box. They're putting a 5 onto the 6 arrow. So this is it. This is where we get the 1, 5 pair here. We get a 2, 3 pair over here. And I really hope that this is going to work some magic. I really do hope. So this now has got to be a 2, 3 pair, which places 1 on the diagonal, places 2 here. We can get rid of some things at the bottom. Oh, and this is on an arrow, so let's not neglect this. If that can't be 2, that can't be 3. This 2 is seeing this cell, so that gives us this one as well, which bounces back up here, which bounces back over here. Good grief. That places 3 on this diagonal, which places 3 and 4 in the middle. Okay, so these... Okay, so 3 is now not here. 4 is now not here, which means 1 is not here. So this is a 1, 3 pair, and this is a 2, 4 pair, and the 1, 3 pair fixes the 1 and the 5. Okay, so now we can get rid of 2 and 3 from this square. So this has to be 1 or 4. We can place the 7 in box 3, and this 1, 4 pair fixes the 5, 4 pair in box 6. So now this column, and this just needs a digit that we haven't got yet. It looks like it's a 5, doesn't it? And this has got to be 1 or 4, and then we can't put 3s down here. And now if you look along there carefully and ask where 3 goes, it has to go into this cell, which places 1 beneath it, 4 on the arrow, 2 above, that's a 2. We've got we've got a 4 on the diagonal. That's fixing the 1s and the 4s. That's a relief. Okay, good. We can get rid of 4s from here, so that's got to be the 4 in box 1. That's the 4. That's the 3. Get rid of some more things over here, and we should just be tidying up now. It's a wonderful puzzle, isn't it? There, with a breathtaking moment, a really breathtaking moment. And why can't I fill this in? Oh, I see, it's the diagonal, isn't it? Of course, I've not done everything I could have done on the diagonal. But once we do that, we should be good to go. 1, 3, 2, check, yay. Beautiful, beautiful. It was a bit of a case of where now for a while, because I didn't really have a good inkling as to how to start it. I'm not even sure if what I found was the best way to start it, but I found a relationship between this domino, didn't I? But really, the trick, I think, is not that. What was the trick? The trick was something. Oh, yes, I managed to get this to be a 9 arrow. Yeah, that was the trick. Yes, these dominoes were the trick. Realising that they prevented these 2 digits from appearing in those 6 cells in effect. And therefore you had to have the 6 over this side, and it couldn't be on the diagonal. It's wonderful geometry. It really is elegant, isn't it? Because it's not monstrously hard at all. It's just difficult to see. And then once you see it, and you can lock the 6 down here, yeah, everything started to flow. But my favourite bit was these arrows. No, it was this one and this one. Let me greenify them, these. And once we realised that this had to be a 4, 5 pair, and then realised it couldn't be double 4 because it would make this one double 5, that was just absolutely icing on a very pleasant cake. So Joseph, take another bow, my friend, and I hope you enjoyed the puzzle. Let me know in the comments. I do enjoy them, especially when they're kind, and we'll be back later with another edition of Cracking the Cryptic.